So I made you a simulation in Igor, and I want you to help me figure out the rules. So I'm going to reset, and you can watch for a little while. And you have lots of things to figure out. So if you watch the collisions with the walls, you might be able to persuade yourself whether those are elastic. Okay, and now I want to see whether it's time reversal invariant. So I got to do this carefully. So notice at the beginning, they all have the same color. And I'm only going to go a little ways and reverse. And see, they had the same color again. And reverse. Okay, this is no fun. Let's go for 100. In the collisions, they may change color because the color is encoding energy. Red is slow, and blue, I guess, is that right? Blue is fast. What are the rules? Are we in agreement that the collisions are elastic? Okay, it doesn't appear that the sort of typical speed is slowing down over time, right? Imagine if the collisions were not elastic. Then on each collision, some of the kinetic energy is going to get lost, and they're going to settle down and be sad on the floor. Right? No. You can hack the code. I'll post it. So, okay, so the rules seem to be, is there gravity? How do you know? Yeah, they seem to be going between collisions pretty much in straight lines. Is this 2D or 3D? How do you know?
Because they always glide if they don't go through.
Yeah, so this is kind of a weird model, right? This is a two-dimensional gas of hard disks, not to be confused with what stores information on your drive. All right, so these are hard disks, they collide. And what do you make of this observation that there seem to be a lot more red ones than green ones? Did I program that in? Yeah, Alex.
Yeah, you started with a bunch of red ones.
Okay, so let's restart it and see. Hang on.
Let's go up into it.
Shut up. Okay, so, well, all right, let's see. Maybe we can do 2. Okay, so the initial condition is not what we're going to see after a while, right? It's pretty bizarre that all of them have exactly the same, yeah? You want a redeeming?
Yes.
Okay.
Every time that you up the number of particles, the total energy in the system stays the same. So when you're upping the mass of like the entire system, that means the velocity is going to go down, and that's why they get closer to red.
Okay, so if I have the same energy distributed over more particles, then the average per particle is going to go down. So the average speed would have, yeah, okay, I guess I see that. So what shape are we getting for what's being plotted here? Hello. What is this? What is the meaning of this frequency? That says energy, so this axis is energy, and that one is frequency. How is that being calculated? Yeah?
The number of particles at each respective speed or energy.
It's the number at any given time, or what?
Yeah, the whole system.
Then the whole system over time, yeah. So the numbers here keep accumulating. For every time step we ask, what is your, in this case, what is your energy? Does it fall in the lowest bin or the next bin or the next bin? And for each one that falls in that bin, add one count to that frequency, and then, you know, divide by the total so you get a normalized kind of distribution. Okay? And anyone recognize the shape that this thing is trying to say? Exponential decay. What's decaying? Is this, so according to his observation, the more energy you have, the less likely there is to be you. That is, you're much more likely to be poor than rich.
Economics lesson.
Isn't that right? So is this capitalism? Yeah. So the fundamental rules of this simulation are just bounce them off each other elastically. I started with a goofy initial condition. And so you see a spike. This is the spike I think Alex was talking about. And that's weird. How come it's in a different color depending on whether we're plotting? Is it? Maybe it's not. No, I think I fixed that. Okay. So this is that initial strange distribution. And so we see the big spike because initially they all had exactly the same speed, or they had, therefore, the exact same energy. And this looks like an exponential, and that, Ian says, looks kind of sort of like the Boltzmann distribution, but the one you did in chemistry was probably for 3D, and this one's for 2D. So it's slightly different. Okay? Yep, but it's in 2 dimensions, and so the shape that we could calculate for that. So what this is saying is, even though all the collisions are perfectly reversible, if I were to now reverse time, would it go back? Okay, so let's try this. Okay, we have a bunch, 100. So I'm going to go for a very short time. Whoops. Does that work? I think I needed to, sorry, let me try this again. Okay, now reverse. We'll see if we get back to all the same color. I didn't see it, did you? Let's try it again. Reverse. Damn. Okay, try again. Reverse. Why doesn't it work? Wait. Maybe it's just a stupid simulation. Okay, so let's go down to 10. Reset. Start. Reverse. Reverse. Reset. Reverse. Okay, there, yay, reverse. It worked. Okay, so yeah, so why is that? Why is it if I have a bunch of particles, a boatload? Look, if you want to crash your own computer, you can do it on your own time, Faith. Why would that be? And importantly, what is that telling us about the arrow of time? So we have fundamentally reversible collisions. But in this simulation, there's a problem that, well, who collided with whom first? Right? And if I play the movie backwards, I might have picked a different one because there was going to be a 3-particle collision. And so I, in the reverse time direction, picked a different pair that was colliding. And therefore, I wouldn't get to the same condition.